Okay.
Mr. Claw?
Go ahead.
Great. So we did our project on the rescue of the USS Enterprise. This was actually our third project in the past couple of weeks. We started with the octocopter, which Amazon stole our idea. Then we switched to the T2 reactor, which ended up being a nightmare. We couldn't get our model to work, so ended up with this project. It was a lot of fun. Pretty quick, short notice. So our project consisted of, our problem statement was that the USS Enterprise had been critically damaged in a battle with the Klingons and had lost power to their life support systems. And so they have sent out a message to all of the surrounding areas requesting help. So this is kind of our own creative take on the aircraft carrier problem. So the USS Hedengren was in the area, decided that they would go and help. The USS Hedengren was equipped with a matter-antimatter reactor, taking the place of the nuclear reactor in the aircraft carrier problem, and then the fusion reactor and deep space batteries. So.
Taking the place of the regular batteries.
Yes.
Obviously, these are far superior. Pen? So we had the 3 transfer functions that were given to us. We didn't change those much. So what we did in our experiment is we just left those transfer functions. But what we did is we tried to get PID controllers that were tuned to give us the optimum performance. So we gave each one a PID controller, and we had our set point as the difference between the demand and our generation. So as we use just the Exxon tuning rules, KP is KC, and 1 over tau for our tau I. And this worked pretty well. So we tweaked it a little bit, but that was pretty much what we went with. How do I change the slide here? That one. Yeah, okay, great.
And we found that of the 3 different power sources that they responded to changes in set points with different response times, the matter-antimatter reactor had the largest power output, but the downside of that was that it took a long time to respond to changes in the load. The deep space batteries, on the other hand, were basically the opposite, that they had a smaller output, but they could respond very quickly. And then another downside is that we couldn't use them for very long because that would deplete their lifetime usage. And the fusion reactor, the equivalent of the gas turbine, was faster than the matter-antimatter reactor, but its demand was limited by our own use on the USS Hedengren. We needed that to power our own systems.
So what we found here is that the optimal tuning parameters for the matter-antimatter reactor was just -1, -1. It was a direct acting controller because as the power increase goes up, the demand difference decreases. So we had our set point at -7. That way, the Enterprise would always be receiving enough power. If we had it set at 0, then if there was a fluctuation, the matter-antimatter reactor wouldn't be able to follow it as quickly. So if we left it at -7, we would be giving more power, but that would ensure that they would always have enough to commence their repairs. The deep space batteries reacted very quickly, so of course their integral term is very high. This is the Simulink integral term, so this is K over tau, which is why that's so large, tau I. And the fusion reactor, their gains were all -1, and that worked very well. And we just changed these just a little bit, these integral terms. Oh, and so these are the resulting plots here. We've got generation and demand here, and this is the demand difference. So you can see that we follow that pretty well. This is 0, this line right here. And so you can see that other than a little spikes here when somebody charges their space iPhone or something like that, we pretty well stay within their demands.
So as you can see, as James pointed out, the Exxon tuning parameters were fairly
fairly accurate. I mean, we didn't have to tweak it at all to maintain a good fit. We did change the integral terms, obviously to account for how they react. The battery's reacting much faster. As James pointed out as well, that it's a direct acting controller. As the load changes, we get the difference goes down as the load goes up. And just hitting it again, the different reactors respond at different paces and different outputs, with the antimatter being the most powerful reactor but the slowest to respond, and the fusion and battery following in suit.
And it looks like formatting wise a little bit got cut off.
Yeah, the battery got cut off, but other than that.
The battery's the
Okay.
fastest.
Okay, good. So this is a smart grid of the future, huh? So we're still going to have fast base load capabilities, and intermediate ones that are going to be a little bit faster, and then energy storage, which is going to be faster. So you guys combine these three to make a control system that can work for deep space.
That's right.
Yeah.
Okay, great.